let's look at electron configuration. So what electron configuration is, it's a way of describing where the electrons are in an atom. So I have this simplified depiction of an atom off to the far right. We have the nucleus in blue in the center. It's got a plus sign because of those positively charged protons that are in the center of the nucleus. Then we have these little green dots are the electrons surrounding the nucleus on different sublevels. So it's those electrons that are constantly moving and orbiting that are hard to define. They're hard to find an address for. So what electron configuration does is it kind of narrows down the area in which these electrons are in. So to figure that out, we're going to use the periodic table as well as a set of quantum numbers. So we're going to take these quantum numbers, define them, and apply them to the periodic table, and then also how they fit into the structure of an atom. So I'm going to start with the principal quantum number. So the principal quantum number is often referred to or represented by the letter N, and you'll see that in the homework quite often. So when I'm talking about the principal quantum number, this is which period of the periodic table we're looking at. So if you notice in the periodic table that I have posted on Blackboard, there's numbers off to the left of the periodic table, and it goes 1 through 7, just how I have them labeled here. And these are representing the periods. So there are 7 periods on the main part of the periodic table. These periods are also the principal quantum number. So n equals 1 would be the first period, n equals 2 would be the second period, n equals 3 would be the third period, so on and so forth. So what we're going to use these quantum numbers as is sort of like an address, a map, if you will. So if I say, okay, the principal quantum number is 4, that means the element that I'm describing, the electron configuration that I'm describing, is of an element somewhere in period 4. Okay, how does that relate to an atom? Well, these rings around an atom are also the principal quantum numbers. So what I mean by that is this first ring would be the n equals 1 quantum level. Second ring would be n equals 2. The third ring would be n equals 3, so on and so forth. So you can keep adding rings as you go down the periodic table. We're going to learn about periodic trends as well towards the end of the chapter. And what we'll notice is that for atomic radius, so the size of an atom, it is going to increase as you go down the periodic table. Okay, and the reason that it's increasing as you go down the periodic table is because as you go down, notice you're adding shells. You're adding rings around the atom. And the more rings that you add, the larger the atom becomes. So that's why the size of an atom gets larger as you go down. So for instance, potassium, this K atom, is going to be much, much larger than a lithium atom, because it's going to have 4 rings around it versus lithium, which only has 2. All right, well, the principal quantum number, it just gives us the period to look in, but we need to narrow it down further, because if we're talking, let's say we're talking about period 3, okay, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different elements to choose from. Okay, so we need to narrow that down further. So that's what the angular momentum quantum number is going to do for us. And this isn't going to be represented by a number, it's actually going to be represented by letters instead. And the letters are going to be S, P, and D. So let's translate this to the periodic table. So when I'm talking about S, we're going to break up the periodic table into different sublevels. The S sublevel is going to be this section here. So it's going to be the alkali metals and the alkaline earth metals, these 2 columns. Excuse me, now when we're talking about the S sublevel, helium actually belongs over here in the S's right next to hydrogen. So the reason helium's over here is because it's a noble gas. Just like all the other elements, in this column. But for purposes of angular momentum quantum number, it belongs in the S block. So that's why I kind of put it there. So this will be the S. Now for the P's, that's going to be this section over here. Not including helium, because helium's over there. Okay, so this is going to be the P block, from boron all the way down to the noble gases. So this whole section. Even draw it again down here so you can see. All right, now the D block is going to be the transition metals. So this whole middle section, so where it says transition elements on your periodic table, that's going to be the D block. And what this is going to do now is it's going to help us narrow it down even further. So if I say the element, the electron configuration that I'm describing is in the 3p area, that means you're going to look in period 3, and then you're going to go over to the P block. So I've now narrowed it down from this entire row to just this section of the row. Okay, so that's how that's going to help us. Now, looking a little bit more further, let's look at these SPD sublevels. So when we're talking about SPD sublevels, these actually describe the orbitals. And what orbitals are is it's an area of probability in which the electron resides. So if you watch the PowerPoints, you can actually see depictions or shapes of these orbitals. So S orbital is spherical in shape, the P orbitals are like peanut shaped, and then the D orbitals look sort of like a clover. So with S, the S block has just one orbital in it. Okay, and each orbital can only fit 2 electrons. So that means since the S block has just one orbital, it can hold a max of 2 electrons. So you don't actually have to memorize this. As long as you have a periodic table, you could figure it out. So if you know that this is the S block, the alkali metals and the alkaline earth metals, how do I know that there's a max of 2 electrons? Because look, you just count 1, 2. Well, let's look at the P's. So the P's block has 3 orbitals. So if it has 3 orbitals, and we just said that each orbital can hold a max of 2 electrons, how many total electrons can fit in the P block? So 2 electrons in this orbital, 2 electrons in that orbital, and then 2 electrons in that orbital, for a total of 6. Okay, if I ever forget that, I'm just going to count how many elements are across in the P block. 1, 2, 3, 4, 5, 6. Now let's do the D's. So the D block has 5 orbitals. We said there can be a max of 2 electrons in each orbital. So that's why the max is 10, because we have 2, 4, 6, 8, and then 10. So 10 total electrons can fit in the D orbitals. If you ever forget that, you can also count. So how many in the transition element section? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's where these numbers are coming from and how they apply to the periodic table. Now what I want to do is I'm going to write an electron configuration representing a neutral element. So we're going to start with neutral elements. And if you watched the last video, you'll remember that when we're talking about neutral elements, the electrons equal the protons. Okay, so I'm describing a neutral element here. So the electron configuration that we're going to start with is going to be 1s2, 2s2, 2p4. So this is an electron configuration. I'm using a series of principal quantum numbers and angular momentum quantum numbers to describe an atom. Which atom am I describing? Well, let's start by looking at some of the properties of this. So these large numbers here, these are my principal quantum numbers. So those are telling me which row I'm looking in. Now the letters are my angular momentum quantum numbers. Now there's one that I haven't talked about yet, and that's these superscripts here. Those superscripts are representing the number of electrons. So I'm going to use this as a map to figure out which element, which atom is being described with this electron configuration. So 1, principal quantum number 1, that means look in period 1. Then it tells me, okay, go to the S block. Here's the S block. This 2 is telling me go to the second one in. Okay, so 1s1 would be hydrogen. 1s2, the second one in, would be helium. So just this section here, 1s2, that's describing helium. Now notice in period 1, there's nothing else. There's only an S block and there's only 2 elements total in period 1. So once you're done with period 1, just like when you're reading a book, you go from left to right till you're done with that line. Then you start at the second line, in this case, the second period. So that's what this number 2 is saying. It's going, okay, now you're in period 2. You hit the S block again. Yes, I do. And it's saying go 2 into the S block. So 2s1 would be lithium, but 2s2 is beryllium. But I'm not done yet. I need to keep going. Where? I'm still in period 2, but now it wants me to go to the P. So the first of the P block is boron here. How far into the P block? It's telling me to go 4 into the P block. So 1, 2, 3, 4. This is describing oxygen because that's the fourth element in the P block. So oxygen is the neutral element that is being described with that electron configuration. Now there's another way to do this, and that is to take the number of electrons and add them together. So why would I want to add together the number of electrons? Well, because I just said this is a neutral atom. So the electrons are going to equal the protons. So let's see, I have 4, 5, 6, 7, 8. So I have 8 electrons, which means I have 8 protons. Well, if I know my number of protons, I know the identity of the element. I just need to look for number 8 on the periodic table. And number 8 is oxygen. So I just double checked my answer. That electron configuration is describing oxygen. Now, let's try to write our own electron configuration given a neutral element. So, erase this guy. Let's do sulfur. So let's write the electron configuration for sulfur. I'm going to write it down here so I have more room. Sorry. So we're going to do sulfur. So when I find sulfur on my periodic table, it's number 16. So it has 16 protons. All right, so when I'm writing the electron configuration, once again, we're using the periodic table like a map. Okay, so we always want to start in period 1 in the S block. So you're always going to start with 1s. So I have 1s, that means period 1, go to the S block. Now the number I'm going to put up here, this is where these maxes for each orbital are useful. Okay, because if I want to go all the way through the S block, I need to know what the max in the S block is. And the max for the S block is 2. So if I write 1s2, that's telling me that I'm going all the way through the S block. So I'm going to helium. Now there's nothing else in that period, so next, once I'm done with that line, just like reading a book, I'm going to go to the next line and read it. The next line starts with a 2, because I'm in period 2. I hit the S block first. I want to go through the S block, because sulfur is where I'm trying to get. Let me highlight sulfur in green so we know when we need to stop. So I want to keep going line by line until I get to this sulfur. So I'm in period 2, I hit the S block, 2s2, because that's the max that can fit in the S block, brings me to beryllium. Now I'm going to keep going in period 2, and I hit the P block next. So I'm going to write 2P. Do I want to go all the way through the 2 P's? I do. I need to get to sulfur, so I have to go all the way through that line to get to line 3. So what's the max that can fit in the P block? Well, we said it was 6. So if I write 2P6, that brings me all the way to neon, right? 1, 2, 3, 4, 5, 6. I'm at neon. Now I'm done with period 2, and I can go to the next line, which is period 3. I hit the S block first, always, and I want to go completely through the S block. The max that can fit in the S block is 2. So now I'm at magnesium. I'm in period 3, I'm in the S block, and it was the second one in is magnesium. So if I stopped here, I would be describing magnesium, but I don't want to stop here because I'm trying to get to sulfur. So I'm going to keep going. When I keep going, I'm going to still be in period 3, but I'm going to hit the P block next, right? So 3P1 would be aluminum. So if I want to get to sulfur, how far into the P block do I need to go? 1, 2, 3, 4. It's the fourth one in. So 3P4 would be describing sulfur. Now I know to figure out this is sulfur, you really only need that last piece of information, right? Because it's saying, okay, go to period 3, go to the P block, and it's the fourth one in. But we have to write it like a map. And when you're writing a map, you always want to start from the beginning and work your way to the very end, including all the steps in between. So that's why we do all this. To double check your work, you just need to count. For neutral atoms, you can count the total number of electrons. So when I add these up, I get 16. Since it's neutral, the electrons are equal to the protons. So it checks out that yes, that is indeed the electron configuration of sulfur. All right, let's try another one. So I'm going to leave this one up. We'll do one more down here, and then I'll show you a shorthand way to represent these guys. Okay, so we just did sulfur. Let's do one a little bit further in. How about gallium? So we're going to go to this guy next, gallium. So the electron configuration for a neutral gallium atom. So if we want to get all the way to gallium, we still have to start at the 1s. Okay, so it's going to look very similar to sulfur at the beginning because we always start in the same place. So it's 1s2 brings me to helium. Then I go into period 2. I hit the S block first. 2s2 brings me to beryllium. I keep going. I'm still in period 2. I hit the P block. I want to go all the way through that P block to the end to neon, so it's 2P6. Then that brings me to period 3. I hit the S block first to go through it. It's 3s2. I'm at magnesium. I'm still in period 3, and I get to the P block, so 3P. Gallium is not in the 3Ps. It's down here in the 4Ps. So that means I want to go all the way through the 3Ps to argon. So that means 3P6. Then I hit the 4 S's. Period 4, S block first. 4s2 brings me to calcium. Now I'm hitting the D's for the first time. So I wanted to do this example for a reason, because there's always a catch. There's always a rule, right? An exception. So for the D's, D's are always one less than the period they're in. So notice I'm writing n minus 1. N being the principal quantum number, and then one less than the period they're in. So if I'm in period 4, once I hit the D block, that means I'm not in the 4Ds. I'm one less, so I'm in the 3Ds. Okay, so more specifically, these are going to be the 3Ds. These will be the 4Ds. This will be the 5Ds. This will be the 6Ds. Okay, this has to do with energy levels and the way orbitals fill. So the explanation as to why these are 3D instead of 4D for this period is a little beyond the scope of the class. If you can just remember that they're always one less than the period they're in, you're good. Okay, so we have 4s2 brought us to calcium. So when I hit the D's, instead of writing 4D, I'm gonna write 3D. Now, I want to go all the way through the D's because I want to get to the P's. That's where gallium is. It's in the 4 P's. So if I want to go all the way through the D's, what's the max that can fit in the D's? We wrote it down here, 10. If you're unsure, just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know I don't have it drawn out there, but you can get your periodic table and count them. There is 10. So 3D10 brings me to the end of the 3Ds. So I'm at zinc. Then I hit the P's again. I'm going to go back up to 4 because I'm in period 4. Now I'm in the P's. And gallium, it's the first one in the 4 P's. So I would write 4P1. Awesome. Okay. Well, now let's look at how to write these shorthand, because that's a lot of writing when really that last piece of information kind of tells you all you need. So how could we write this or make this a little bit shorter? So how we do that is called the noble gas shorthand. So for the noble gas shorthand way, what you can do is you start with the noble gas. So instead of starting at 1s, like we did for both of these examples, you start at the noble gas in a row above the element or atom you're trying to describe. All right, so let's take sulfur here. So this is sulfur, and we're going to write the shorthand way. All right, so in order to start writing the noble gas shorthand configuration of sulfur, we want to start at the noble gas in the row above sulfur. So here's sulfur. It's in period 3. So that means I'm going to start with the noble gas in the row above it. And remember, the noble gases is this last column here. So the noble gas in the row above sulfur is neon. So I'm going to start with neon. I'm going to put it in brackets, Ne in brackets. That means instead of starting at the 1s, I can start here at neon. So from neon, then I'm going to go to period 3 next. So I get 3 S2, and then I'm still in period 3. I hit the P block, and it's the 4th one in. So that's the shorthand way for sulfur. Now notice when I wrote Ne, neon, that took care of this whole section. Okay, 1s2, 2s2, 2p6, because period 2, the P block, and the 6th one in described neon. So I didn't have to write that. Instead, I just wrote Ne, and then wrote the rest of it after that. All right, well, let's look at the noble gas shorthand of gallium. So let me move this up a little bit. So we're going to do the same thing. We're going to start with the noble gas in the row above. So gallium is in row 4. So we're going to look at the noble gas in row 3. So we're going to start with argon. Now argon is representing this whole section here, all the way through 3p6. Period 3, P block, 1, 2, 3, 4, 5, 6th one in is argon. So I just cut out that whole section by writing AR in brackets. So now I need to still, however, include this second portion. So I still need to write 4s2, 3d10, 4p1. So that would be the noble gas shorthand of gallium, a neutral atom of gallium.